Actually, when your acceleration is not uniform, there's little pieces of uniform where you would do it bit by bit. We're not going to worry about that. For the math, we're going to use uniform acceleration. It's the simplest form of acceleration. It occurs whenever there's a constant force acting on an object. So if you're pushing a wagon, but you were pushing that wagon with the exact same force and you kept going faster, faster, you're not like putting more force and less force. If you were to somehow, at least for a period of time, 10 or 20 feet, just push it with a very precise force, that will give you a uniform acceleration. We're going to be concerned with uniform acceleration quite a bit for this class. It's just, it's a good example, and the math is doable. So, especially in the beginning. Most of the examples we will consider will involve constant acceleration, right? When things are falling, they're falling at a constant rate. They're falling faster, 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 because gravity is the same force of gravity as pulling. So if you ever want to get uniform acceleration, just drop something. It's falling, gravity is pulling, 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 but the gravity is at the same rate. When you're down at the surface of the earth, of course, if you go up, high in the sky, gravity actually gets weaker. Yeah, it works that way, right? Like, the farther you get from Earth, the weaker gravity gets. You have to go really far, though. That's another class. Yeah, so the acceleration does not change. Your velocity is changing but it's changing but the acceleration doesn't change. It's a uniform acceleration. So here we have acceleration versus time, right? Before, the first graphs we had were distance over time, then we have velocity over time. Now we have acceleration over time. When it's uniform acceleration, the acceleration doesn't change. Your velocity is changing, your distance is changing, time keeps changing, but the acceleration is not changing. Okay? Don't worry, we'll have math problems that'll help you with this. Okay, so now the velocity graph for uniform acceleration is a straight line with a constant slope. The slope of the velocity graph is equal to the acceleration. Okay, so what they're saying is that here, your average velocity is the difference between, right, your initial velocity, wherever you started the chart measuring, and your final velocity. Well, the average is going to be in the middle. So that's not too bad, right? That's pretty easy to understand. If you're accelerating and you want to measure your acceleration over a period of time, well, your whatever speed you were going when you started, and then whatever velocity you are when you stopped, right? The average is going to be in the middle, okay? So here is another mathematical equation. All right, math. The universe is mathematical. It's scary how we can model the universe using math, right? So acceleration, remember delta is a change, so a change in velocity over time. Now look what happens. If we know what the acceleration is and we know the time, well, you can solve for velocity, right? This equation algebra, if you multiply both sides by t, right? Multiply both sides by t, the t we cancel here, then delta velocity is equal to acceleration times time. Okay? And now look at this. Now if say you're already traveling at 20 miles an hour when you start your measurement, and then you're going to measure, right? And then you start measuring, then you accelerate for a bit over some period of time. Well, what's your final velocity going to be? Well, it's going to be the initial velocity plus the velocity you got, the increased velocity you got from acceleration. Here we have AT. Well, look, right here, it's telling you AT is equal to the change in velocity. So you just put it there, see? I know, folks, there's a lot going on. That's why you read, right? You can pause this video, go get a drink of water. I'm having too much fun. Oh no, what happened? That's okay, I don't want to do that one anyways. More graphs. There's one more graph I wanted to do, which is this one. Okay, this is the one I wanted to do. Right. For a no, actually I want to go back. Let me go back. Did I want to do that one? This is the one I showed you. And no, I didn't want to do that one. And okay, let me show this one. We'll talk about part of this. Okay. Let me get these in here. Your average velocity, remember I said that that is, from the other graph, it was 1/2 v, if you go back a couple slides. Well, then also it says that your velocity is equal, if you multiply acceleration by time, that gives you velocity too. So your velocity is also equal to 1/2 your acceleration times your time, right? Now distance, so if you multiply acceleration by time, you get velocity. But look what happens. If you multiply velocity by time, you get distance. Now we're back where we started this whole PowerPoint series at. We started at distance, went to velocity, went to acceleration, but you can go back the other way. And then distance, say you know your acceleration and you know your time, you can figure out your distance. It's 1/2 AT squared, right? Because you have your velocity, which is this, times your time. So it's this time times this time, AT squared. So when you're doing the math, you want to think about where did these equations come from, right? There's a tendency to want to just plug them into a formula, but you want to think about where they came from. Now here, here's velocity over time, right? So if you were going some velocity over some times, the distance would be the area of the curve. And watch this. This is clever for those of you that really like math. Here, if you did from 0 to v0, so this is a rectangle. Well, it's the area of a rectangle. It's one side times another side. So here you have v0, which is this distance, times t, which is this distance. That gives you the area under the curve, which is distance. And now here, if you accelerated, so here your velocity is changing over time. It's increasing uniformly. Well, this triangle, right, what's the area of a triangle? It's 1/2 rise over run. Well, 1/2 of your v minus v0, so that's this portion here, right? And this is that triangle, so it's 1/2 AT squared. Remember, for distance, we went to the previous chart. For distance, oh no, oh yeah, I gotta do this. It's AT squared. Velocity is 1/2 AT, but then for distance, you take your velocity and you multiply it by time, so it's 1/2 AT squared, okay? So the total distance, if you were going at some initial velocity and then you added some acceleration, would be v0t plus 1/2 AT squared. So this is a formula that we'll be using in the homeworks, okay? Yeah, and then this part here is for the acceleration. I already said that. Okay, and that is it, folks. I know there's a lot there. Trust me, I know that. But go over it, read the book, right? And we'll be doing some problems. Goodbye.